Welcome, and thank you for joining us for today's webcast, Removing Thermal Bottlenecks with Passive Thermal Solutions, sponsored by Advanced Cooling Technologies and Tech Briefs Media Group. I'm Billy Hurley, Digital Editorial Manager with Tech Briefs Media Group, and I'll be your moderator today. Our webcast today will last approximately 30 minutes, and there will be a question and answer period at the end of the presentation. If you have a question, you can submit it at any time during the presentation by entering it in the box at the bottom of your screen. Our presenters will answer as many questions as possible at the conclusion of the presentation, and those questions not addressed during the live event will be answered after the webcast. In order to view the presentation properly, please disable any pop-up blockers you may have on your browser. Now let's introduce our speakers. Dennis Pamukju joined ACT in 2014 as Product Design Engineer in the Custom Products Group. Dennis has served as the technical lead on a variety of programs, successfully providing thermal management solutions to a variety of commercial and defense customers. Currently, Dennis is responsible for new business development in the northeastern U.S. territory. Also on the line today is Greg Heshley. Greg Heshley is a product development engineer in the Industrial Products Group. He works directly with customers to conceptualize, design, and analyze thermal solutions for electronics, medical, LED, industrial, and other technical markets. With almost 3 years of experience in the Industrial Products Group at ACT and 5 years as a fuel cell systems engineer at Ballard Power Systems, Greg has cultivated a broad technical background and has extensive experience designing, building, and managing a variety of programs. So now I'd like to hand the webcast over to our first speaker today, Dennis Pamukju. Dennis?
Thanks, Billy. So to begin today, we're going to talk about what is a passive thermal management solution, what does that entail, and talk about some common passive thermal management tools. Next, we'll focus on heat pipes and HIKT assemblies as passive thermal management tools and dive into where they're used and why they're used. Finally, we'll conclude today's presentation by talking a lot about how to design as well as model heat pipes within your system. But first, I'd like to talk a little bit about Advanced Cooling Technologies. We were founded in 2003 in Lancaster, Pennsylvania, and have been profitable and growing since. To date, we are over 115 employees and have grown our facility to over 60,000 square feet. We hold our core values to be innovation, customer responsiveness, and teamwork, and we serve industries comprised of the defense and aerospace as well as industrial and custom products. We have strong roots in R&D. We've won a variety of awards for commercializing some of the technologies that we've developed as part of working on R&D programs with the government sources such as DOE, DoD, and NASA. ACT, no matter where you are in your project, we can likely help you when it comes to thermal and mechanical modeling of solutions. So we work with our customers at the very front end to help them do feasibility analysis, do the detailed thermal and mechanical modeling required to produce the solutions, and then prototype and test those solutions before moving into full-scale manufacturing. Feel free to reach out to us for your thermal needs. So now let's begin by talking about passive thermal management. What is passive thermal management? In the design of electronics assemblies, conduction and convection are the primary modes of heat transfer. Thermal solutions in which no additional energy is used by the system to reject the heat that's generated from the device in it doing of its function are called passive solutions. Thermoelectrics, fluid pumps, and even fans are examples of active elements. So what is the benefit of using a passive thermal management solution? Well, as mentioned on the previous slide, if we don't have to input any additional energy into the system to remove the heat, then the energy consumption for the overall system is decreased. In addition, removing some of the elements we discussed, such as pumps, thermoelectrics, and fans, will reduce the overall complexity of that system. In most applications as well, weight can be reduced by optimizing the passive solution to dissipate the heat. All of these items are focused to help increase the reliability of the overall system, which is inherently why a lot of engineers turn and begin to look at passive thermal management solutions. So what are some common reasons for passive thermal design? The first would be where you're trying to ruggedize your design to be used in some industrial setting. Elimination of fans and pumps inherently make the design more simple and able to survive in a rugged environment. Next would be if you're designing for an RF and or airtight enclosure. Typically, these are used in aerospace and defense industries. Passive thermal management can help you seal that box or the assembly and still move the heat to the external where it can be dissipated to the ambient. The third reason we see customers use passive designs or engage and want passive designs is when noise and vibration are undesirable in the final product. For instance, in some laser optical applications where you don't want vibration from pumps and fans to be transmitted to the system, customers will look at passive thermal solutions to help move and spread that heat effectively so it can be dissipated to air without the need for fans and or fluid pumps. And finally, we see customers come to us when their system is already coupled to some liquid loop. However, either the cost or the maintenance associated with chilling that water and pumping it through their system has increased to the point where they are looking for their next generation device to be decoupled from that liquid chiller. Let's talk a little bit about passive technology options. The most basic passive thermal management is done through large metal conduction heat sinks. So this is typically the most elegant and the most straightforward way to manage thermal loads within a system. As long as your system can afford the higher delta T's, which are going to be associated with standard conduction, this is one avenue that you can pursue. If there's flexibility required for the system, thermal straps are also a good way to passively move thermal loads from one location to another. Again, as long as your system can tolerate the higher delta T's associated with this type of solution. We're going to focus most of the presentation today on copper water heat pipes. This is passive two-phase heat transfer and is typically used when you need to enhance conduction or when you need to move heat from a source to your ultimate sink. Heat pipes can have other working fluids as well and other envelope materials. And those are good options in different types of ambient environments. A vapor chamber is essentially a heat pipe in a different form factor. Vapor chambers are excellent to use when you have high heat flux. The larger area and vapor area inside the vapor chamber will allow for a high degree of spreading. And again, these are high performance devices that should be used when you have very high flux heat loads. The final technology we're talking on this slide about is phase change materials. Phase change materials are waxes that melt at very defined temperatures. These can be used in conjunction with aluminum housings to create essentially thermal batteries that can store heat for a defined period of time. Finally, I'd like to give some considerations when using passive thermal management. Typically, enhancing conduction is key to increasing heat transfer. Any time that you can increase the conduction, you're going to be able to move more heat from one location to another, which is going to drive down the temperature on your ultimate device. In most passive designs also, air is your ultimate heat sink. Whether it's a natural or forced convection environment, putting more air into the system is going to result in more heat transfer away from the system. And finally, in passive thermal management, your device will never be cooler than the ambient temperature in which it's being used and operated. So if you do need your device to operate at a temperature below your ambient temperature, you're going to need to look at an active cooling solution. Let's begin now to take a deeper dive into heat pipes and HiK assemblies. We'll begin with some theory about heat pipes. Heat pipe is essentially a sealed copper tube with a small amount of working fluid on the inside. In this case, a copper water heat pipe has a copper envelope, and the working fluid on the inside is water. Along the inner diameter of that tube is a porous copper wick structure. You can think of this as a copper sponge. So how does a heat pipe work? Well, any heat input into the pipe is going to cause the working fluid on the inside to vaporize and find a cooler part of the pipe to condense into. When it condenses into the wick structure, it will let off its latent heat. That wick structure then is going to passively pump that fluid back to your evaporator, creating an internal closed loop. Due to the two-phase heat transfer, a heat pipe is a superconductor of heat. A well-designed heat pipe that can take the heat load is going to have a 2 to 5 degree delta T across the length of the pipe. Copper water heat pipes are very high performance due to the properties of water. They can typically accept up to 50 watt per centimeter squared heat flux from a device that they're attached to, and they're very reliable. In fact, heat pipes have been used in your laptop for many decades now. At ACT, we have demonstrated manufacturing capacities of over 250,000 heat pipes per year, and we build a variety of different style heat pipes to meet our customers' thermal and mechanical needs. So each heat pipe can be bent, flattened, and shaped and fit into your assembly to meet your requirements. In addition, we've designed and built and launched heat pipes for space applications. Heat pipes are freeze-thaw tolerant, shock and vibration tolerant, and when they're integrated into your next level thermal assembly, they're also MIL 810G certified, and we can pass those MIL 810G testing requirements. So a HiK assembly is essentially where you take a heat pipe and you integrate it into an aluminum or other base metal conduction plate. So HiK is the term that ACT has created for high thermal conductivity by embedding heat pipes in aluminum plates. When you do this, the effective conductivity of that aluminum plate will range anywhere from 500 to 1200 watt per meter K. For reference, the conductivity of aluminum is about 200 watt per meter K. So, you basically, by embedding a heat pipe inside an aluminum plate, you can have a higher conductivity, 3 to 5 times that of aluminum, with the same weight and the same structural strength as your aluminum. As part of the design process, all the critical features can be maintained. ACT has demonstrated making HiK plates with fully embedded heat pipes as thin as 1.8 millimeter. Here's a quick example of a HiK plate thermal simulation compared to that same plate with the same boundary conditions made in just aluminum. As you can see, the image on the left shows the aluminum plate, and you can clearly make out that there are 3 locations of heat input on this plate. The boundary conditions on the sides, those thick blue lines, represent a 32-degree constant liquid-cooled rail. So the idea here is that we're trying to pull heat from those devices out to that liquid-cooled rail. In the HiK assembly, by embedding heat pipes, we were able to reduce the thermal resistance through that plate. Thereby, we were able to increase the conductivity of the plate and drop the temperature of those components by about 20 to 30 degrees. There are a lot of ways that you can use heat pipes embedded into aluminum plates. The first we're going to talk about is HiK heat sinks. So this is where you have a heat sink and some device mounted to the bottom of this heat sink that's trying to dissipate its power to the air. By embedding heat pipes, we're going to get better spreading through the base of that heat sink and better fin efficiencies on the air side of the heat sink. We can also integrate heat pipes into board frames. These HiK frames are used in electronics assemblies and coupled with PCBs. The skyline of the components on that PCB mate to the HiK frame. The power from those components is moved to the edges of that board where it's locked into a chassis. Heat pipes can also be used in those chassis as well, whether in the side walls or top walls, to move heat to the next level thermal solution. Next, let's take a look at some design and modeling principles that will help you utilize heat pipes as part of your next design. So the first step of solving any thermal problem is to lay out your thermal resistance network. This shows you the path that the heat is going to need to take to get from your device to the air. Now, when you're doing this design, a heat pipe can be easily integrated into your network and assumed to be about a 2 to 5 degree C rise element. If you lay out your overall network and this heat pipes make sense, then it makes sense to move to your next step and begin to assess the feasibility of using a heat pipe. This next step is going to be to look at the power transport capacity of the heat pipe that you're going to need. So the transport capacity for a heat pipe is governed by a variety of limits. For most terrestrial applications, we're interested in the capillary limit. This limit is when the heat pipe fluid inside the heat pipe is being returned to your evaporator through the wick structure. The heat being put into your evaporator is high enough that it actually causes that fluid to vaporize from the wick structure before it reaches your device. The limits are a function of the diameter of the heat pipe, the length of the heat pipe, and the orientation in which the heat pipe is used, as well as the fluid properties and wick properties. To try to size your heat pipe, which is the first step you need to take after you've decided to use one, ACT offers a free online calculator that you can use. There's no registration required. To find this tool, simply navigate to our website, one-act.com, click on Resources, click on Calculators, and Heat Pipe Calculator. When you do that, you're going to find an image as well as some fields for input. The input fields are the length of the heat pipe, the length of your evaporator, the length of the condenser, and the orientation of the heat pipe with respect to gravity. In this example, we're looking at an 8-inch long heat pipe with a 2-inch long evaporator, 2-inch long condenser, operating horizontally, or 0 inches against gravity. Reading this chart is fairly simple. Let's, for instance, take that we have to move 50 watts, and we'd like to know what heat pipe will help us move 50 watts. And we know that our device is going to operate somewhere between 60 and 80 degrees Celsius. Looking at this chart, we can see that a 6 millimeter heat pipe is able to move that 50 watts across our operating temperature range. If the 6 millimeter heat pipe is not going to be able to mechanically be packaged into your assembly, you could also look at this chart and see that 2 4 millimeter heat pipes will also move that required amount of power. Now that you've determined the diameter of heat pipe that you'd like to use, you're going to have to integrate it into your solid model. Heat pipes can be bent. Typically, we recommend that the minimum bend radius is 3 times the outer diameter of the heat pipe. This bend radius is taken from the center line of the heat pipe. Heat pipes can also be flattened without reducing their transport capacity. You can flatten a heat pipe down to 2/3 of its outer diameter without significantly impacting how much power it can carry. For instance, a 6mm OD heat pipe can be flattened down to 4mm height without reducing its transport capacity tremendously. The heat pipe is going to be attached to your assembly either via a solder or an epoxy. Solder has a little bit higher conductivity, and but the epoxy is a little bit easier to work with. Just some things to keep in mind during your design. And finally, we like to mention that the interfaces between the heat pipe and the source and sink are critical. Most of the time, when it might seem like a heat pipe is not working, it's because there's some problem at the interface that's creating a lot of thermal resistance. Make sure that as part of your design, you have to look at these interfaces and make sure that they're robust. Now let's talk about one way to do some very basic high-level thermal modeling. After you've bent and flattened your heat pipe into your system, we're going to make it a solid rod, one element, and assign to it a thermal conductivity value. We suggest that you begin with about 10,000 watt per meter K. Run your model and check the temperature across that solid element. Keep iterating and increasing or decreasing that conductivity value until that maximum temperature difference across the heat pipe is between 2 and 5 degrees Celsius. We're going to compare this basic modeling approach to the more detailed modeling approach that we're about to talk about at the end of this presentation. In the more detailed modeling approach of a heat pipe, we're going to divide the heat pipe into two solid elements, the heat pipe envelope and the vapor space. The envelope, it captures all the radial thermal resistances, including the thermal interface material, so your solder or your epoxy, the heat pipe wall resistance, the heat pipe wick resistance, and the evaporation condensation thermal resistance. This envelope element is going to have a fairly low thermal conductivity. The next element is the vapor space, and this simulates the effect of the two-phase heat transfer occurring within the heat pipe. This is going to have a fairly high thermal conductivity. So let's look at an example where we need to transfer 25 watts at room temperature against gravity. We run our heat pipe calculator with the values, and we find that a 4mm heat pipe, it will work for this application. So now that we have this 4mm heat pipe, we're going to calculate the effective conductivity for the thermal interface, wall, and wick portion of this model. Looking at the solder, the copper wall, and the wick evaporation and condensation resistances, we plug these into our equation, and we get an effective conductivity of 26.7 watt per meter Kelvin. To simplify the meshing, you can add those thicknesses and assume that the entire wall, wick, and thermal interface material for this heat pipe is going to be about 0.04 inches thick. Next, let's look at the vapor space. We're going to use Fourier's law to determine the effective conductivity for the vapor space. Knowing again that we want to move 25 watts, we know the length of the heat pipe, and we know the area of that vapor space inside, we can calculate the effective thermal conductivity. As you can see in the calculation, we come out to about 233,000 watt per meter Kelvin. So at this point, we've confirmed that the heat pipe is going to move the amount of power required by using the heat pipe calculator. We've incorporated it into our solid model by bending and flattening it. And now we've determined the effective thermal conductivity for both the heat pipe wall, wick, and thermal interface material, as well as the vapor space. The last step is to assign your boundary conditions in your FEA model and run. Next, let's talk about HiK plate modeling. As we mentioned before, the bulk conductivity for a HiK plate is somewhere between 500 and 1200 watt per meter Kelvin. This depends on geometry and your sink conditions. To model a HiK plate, take your plate as modeled in aluminum and change its effective thermal conductivity to 600, or somewhere within that 500 to 1200 range. If that gets you close to your desired thermal results, ACT can likely work with you to optimize that heat pipe design to meet your goals. Finally, let's take a look at how these approximations, the complex modeling, compare to the actual tested device. On the left here, we have a part that's about 3 inches by 5 inches, and there's a heat source. Applying an effective conductivity to this part of 500 watt per meter Kelvin gives us a maximum temperature of 83.7. Using the 2-part heat pipe modeling approach, we get a maximum temperature of 81.3, as seen in the middle image. And finally, when we built and tested this part, we got a maximum temperature of about 80.2. As you can see, the error is not very large from our tested part to the 2 different modeling approaches that we used. So I hope that this shows that you can model and design a heat pipe into your assembly and have good confidence that you're going to get the results that you anticipated. So in summary, passive thermal solutions reduce energy consumption, weight, and complexity of the overall assembly while increasing reliability. Heat pipes and HiK assemblies are just 2 examples of passive thermal tools that can be used in your design. And the mechanical modeling and FEA analysis of these tools can be completed with a high degree of certainty by an engineer who knows how to use thermal modeling tools. I'd like to point out a few resources that are available on our website, including our copper water heat pipe calculator and a library of webinars that we've done in the past. Thank you again for listening to this presentation. We hope it's been helpful. And I think at this point, I'd like to bring my colleague, Greg Heschley, back to answer some of your questions.
Thanks, Dennis. At this time, we'd like to begin our Q&A. So if you have a question out there, you can submit it by entering it in the box at the bottom of your screen. And I'd like to welcome Greg Heschley to the line. We have a few questions here. The first question I see, my device needs to operate at 10 degrees C. Would I still want to use a water heat pipe?
At 10 degrees C, water would still work. That's certainly above the freezing point of water, so it would still work. It might be better to use methanol for that temperature range, though. So that really depends on the application, whether you would go with a water or a methanol or other fluid solution. But certainly both of those could work at those temperatures.
Greg, what distance can a heat pipe transport heat against gravity?
We normally say the max distance against gravity that a heat pipe can transfer is about 9 inches. That being said, it depends on the wick geometry and how we select those properties. In addition, you can daisy chain heat pipes together if the application requires a height higher than 9 inches. So you can basically string heat pipes together to get that height if needed.
Here's another question. What is the performance difference between a fully embedded and a partially embedded heat pipe? Interesting.
In a fully embedded heat pipe, the heat is going to be entering the heat pipe around the entire diameter, which reduces the heat flux into the heat pipe. So what we would expect in a fully embedded heat pipe is a lower delta T for the entire heat pipe compared to a partially embedded heat pipe.
And this will be our last question today. Can vapor chambers be integrated into aluminum plates?
Vapor chambers can be made into aluminum plates. A copper vapor chamber could be bonded or soldered to an aluminum plate. But in general, we prefer to embed heat pipes into plates for most applications. We see that for 2D spreading with lower heat fluxes, it's really best to use heat pipes for that type of solution.
All right, we'll end it there. That concludes today's webcast. Again, if we did not get a chance to answer your question today, our sponsors will do their best to address them after today's presentation. So our thanks to Dennis Pamukchu, Greg Heschley, and everyone out there for joining us today. And just a reminder, this webcast will be available on demand at techbriefs.com for the next 12 months. Have a great day.